Good evening, everyone. My name is Renu Raman Sahu, and today we will be discussing some of the questions of the assignment of this week. So, let us go to the first question. Let us go to the first question now. So, the question it is asking is from the following statements, choose the correct option related to the qubits. The two orthogonal z-basis states of a qubit are defined as 0 and 1, 0 ket and 1 ket. Yeah, so this statement is true. Why? Because so this z-basis states, these are basically the eigenstates of the Pauli spin uh, operator in particularly this sigma z component, and it is nothing but this identity matrix. And this will have eigenstates 1 0, which is defined as 0, and 1 it is defined as like this. Now for the x basis states we have to take the uh, eigenstates of the sigma x operator, which is nothing but 0 1 1 0. And if you want to take the eigenbasis, so the way you have to do is, so let us find the eigenvector and uh, eigenvector and the eigenvalues. So basically we have to find the eigenvectors. So what we have to do is sigma x minus lambda times identity, and we have to take mod of that. It is, so you'll get this operator. So lambda square minus 1 is equal to 0, which will give you the eigenvalues plus minus 1. Now let us say that the eigenvectors are, let us say that eigenvector is, this is the eigenvector, so that will correspond to, so if you operate with sigma x 0 1 1 0, then you should get eigenvalues plus minus, and this is the same eigenvector as a result of the operation. So what you get is y x is equal to plus minus x y. So corresponding to the eigenvalue plus, if corresponding to the eigenvalue plus 1, what you will have is y equal to x and x is equal to y. So the two components of this vector x is equal to y. So if this is x, this is y, so this is nothing but x x, I mean because y is equal to x, and we have to normalize this. So if you normalize this, it will just x will become, so x square plus x square is equal to 1, so that will give you 1 by root 2 1 1 after normalization. Similarly, you can find for so this eigenstate is corresponding to, yeah, so we found that the eigenvector corresponding to plus 1, when eigenvalue is this, the eigenvector of 0 1 1 0, this is sigma x, and one eigenvector we found out, it is 1 1, it is 1 by root 2. This can be written as 1 by root 2 1 0 plus 0 1. So this is nothing but 1 by root 2 0 cat plus 1 cat. Now similarly we can find what it will be for minus 1. For minus 1, sigma x xy will be minus of xy. So it is 0 1 1 0 xy. This is minus x minus y. So yx is equal to minus x minus y, which implies x is equal to minus y. So the vector eigenvector xy will nothing but x, and y is actually, you see, y is minus x, so minus x. So now you can normalize it. If you normalize it, x will turn out to be 1 by root 2. So normalization. So normalization is nothing but this the first element square plus second element square should be equal to 1. So it is x square plus x square equal to 1, which will give you x equals 1 by root 2. So normalization. So 1 by root 2 1 minus 1. So this you can just write 1 by root 2 1 0 minus 0 1 is equal to 1 by root 2 0 minus 1. So for sigma x, the orthogonal basis, okay, we can check if these two states are orthogonal or not. And this state, since it corresponds to minus 1, we can write it as like this. So for orthogonality, we have to check what this turns out to be. Okay, so we have to find this dot product, and this should give us 0. So for minus, so this is bra of minus, so what we have to do, 0 minus 1 by root 2, and this is 0 plus 1 by root 2. And we know that 0, so these are, so 0 1 is 0, 1 1 is 1, and 0 0, this is 1. So if we use this, then what we will get is 1 minus 1 by 2, which will be 0. Okay, so since these two states, the dot product of these two states is 0, we can say that these are the orthonormal basis of the x basis states, and they are orthogonal. So since we found that these two are the orthogonal, so these are not the orthogonal basis. So if there are n qubits in a quantum computer, then it will have n square different states. So this statement is wrong. Why? Because why this statement is wrong? Because it is actually 2 to the power n different states. So for example, so let us try to understand that one. So let's say there are n qubits of a quantum computer. So let us say that there are n qubits of a quantum computer. So the first qubit is, let's say there is only one qubit. The one qubit can take either state 0 or state 1. So this is single qubit, and number of state is, there are 2 orthogonal states. Now let us say there are 2 qubits. For 2 qubits, the possible arrangements are, so 0 0 0 1. So the first qubit can take value 0 or 1, and 1 0 and 1 1. So here see there are 4 states. This is 2 to the power 1, this is 2 to the power 2. If there are 3 qubits, so it will be 0 0 0 0 0 1 and so on up to 1 1 1. So the way to calculate this is, let's say there are n qubit, okay, n qubit there. So in a particular state there will be n such values, and each of these value can take either 0 or 1. So there are 2 ways. So this can be filled in 2 ways, this can be filled in 2 ways, and there will be n times such value. So the number of state will be 2 to the power n. Okay, so this statement that it is n square, so this is wrong statement. Now only correct statements are A and B. So this is your correct answer. Let us go to the next question now. With regard to the normal reflection and Andreev reflection, choose the correct statement from the following. So we can just look at what is this normal reflection and Andreev reflection. So we have a normal conductor and a superconductor. And one electron is coming into this towards this interface. It will have some momentum and some spin it will have. Now in a normal reflection, what will happen? In normal reflection, the electron will follow the law of reflection, just like in optics, that this incidence angle equal to angle of incidence equal to angle of reflection, and that these 3 lines are in the same plane. So here the energy and momentum, and the charge conservation, everything is valid here. Okay, so but in Andreev reflection, what will happen? So an electron will come to, this is normal and this is superconductor. So this will come here, and at this interface, instead of an electron coming this way, a hole will go through the exactly same path. And here what will happen, that electron will there will be an electron here, so there will be Cooper pair formation over here, and that Cooper pair will go in this direction. Okay, so here so you will see that the conservation of charge in both normal and Andreev reflection, so this has always to be satisfied, and energy has also to be satisfied, and so all the conservations law, they has to be satisfied here. So your correct answer will be all of this. And here what you see is like how this law of charge is conserved. See, only one electron is there, and after the reflection only one electron is there. Here what you see is, initially one electron was there, and so okay, this might be unclear. So initially in Andreev reflection, one electron is coming towards this. This is normal and this is superconductor. So only initially one electron was there. After reflection, what will happen? After reflection, the situation is one hole is going towards here and a Cooper pair is going in this direction. So one hole and this electron, they will nullify each other's charge, and what you have is effectively a single electron. So charge is conserved. Fundamental. So energy is conserved in both of these. Okay, here see, here before reflection energy. So whatever the speed of this electron, that would be the speed of electron after the reflection. So energy is conserved. Here you see the energy of this electron, whatever be the energy of this electron. So this is the energy of one electron, right? So here this is energy of two electron minus energy of this absence of electron. So you have to subtract the energy of this from one of the energy of this. So it is effectively the energy of one electron. So this energy conservation is satisfied. And the spin also for before and after, whatever with the spin, that spin is also conserved. So whatever the spin of electron before reflection, the same will be the spin of the electron after reflection. It is in the normal. And in case of Andreev reflection, whatever be the spin here, so what one will be the spin up spin here, and in a Cooper pair the other will have to be the down spin. And since one electron has this down spin, the absence of that electron, it will create an up spin. So the spin will also be conserved here. So with regard to normal and Andreev reflection, all the so all of these are satisfied. Like, I hope this point is clear. So your correct answer has to be this, all of this. Let us go to the next question now. Which of the following is true regarding the relation between phase of BCS wave function and the number of occupied pairs? So the for a BCS wave function, so a BCS wave function is this product over all the momentum states, and UK is the probability amplitude that a Cooper pair of momentum K is occupied, and Vk is the probability amplitude that the Cooper pair with momentum plus and minus K is there. So this represents a two particle state and the two electron state, and the two electrons are basically the Cooper pairs. And so this is it, and it always satisfies this relation. uh, See, phi BCS, this is not an eigenstate of this number operator. It is the eigenstate of a phase operator. Okay, but if there is some uncertainty, you can always prove that the number uncertainty in number and uncertainty in the phase, this always turns out to be greater than or equal to 1. So your correct option is this one. To measure very tiny magnetic fields, which of the following instruments is most useful? So, to for very small magnetic fields, what we uh, it is always the squid. Squid is helpful in. Um, yeah. Squid is a very sensitive instrument which can measure a very tiny magnetic field. So it can measure like yeah. Yeah, so squid is basically superconducting quantum interference device. Okay, and this can measure as low as 10 to the power minus 14 Tesla. Yeah, it is really very sensitive, and this is the most useful instrument to measure very small magnetic fields. So here the next question, in a mixed state of an isotropic type 2 superconductor, the vortex lattice has a triangular symmetry. So that means it will have, these are the vortices. So these are the confined regions in which the magnetic field is there. So this is the region uh, uh, between the when the critical field is uh, between the upper critical field and the lower critical field for a type 2 superconductor. So this has this triangular symmetry. These are the vortices of the in that. Uh, these are the vortices in the superconductor of the type 2 superconductor, and it is in a mixed state. So what it is asking, choose the correct expression for the average internal flux density B, and A is the lattice constant. So that means we are saying that this is A, this spacing is A, and since it is triangular, it is A, and this also is A. Okay, so we can choose a particular lattice. So the way we can choose is maybe this one. And each of these has a magnetic field, magnetic flux density, magnetic flux is phi naught. So what we can do is to find the flux density. We choose a triangle. Let's say we choose this triangle, we are choosing. So we want to find what is the flux density in this area. So that will be the flux density in the entire lattice, because it is uniformly the uniformity of the lattice will translate. So the way to do about it is, so B is equal to area of the triangle. Let's say this triangle is A, B and C. So area of triangle ABC and flux in the area of triangle ABC. Let us first calculate what is the amount of flux. So if you look at, so let us assume that it is a circular geometry, and this is the, so we are looking at this particular one, this particular vortex. So here this angle has to be 60 degree because it is an equilateral triangle. So if it is 60 degree, so the fraction of flux which is going through, which is in the area of this triangle is 60 over 360 degree. Okay, so this is the flux coming from only this B, and we have 3 such vertices, so we have to multiply with 3. Okay, so this is the total amount of flux from vortex A, vortex B and vortex C, the total flux through this triangular area. Now the area of this triangle, so this is an equilateral triangle of side A. So the area of the equilateral triangle is root 3 by 4 into side square, which is A square. Okay, this is the formula for area of the triangle. Now we just have to evaluate this. So it is 3 phi naught, and 60 by 360 is 1 by 6, and this is root 3 into 4, and this is A square. So we have, so this will cancel 2, 3 and is 3 by 3, so it is 2 by root 3 pi naught over a square. So your b is basically 2 phi naught over root 3 a square, so which is this. So this is your correct answer. Let us go to the next question now. In a Josephson junction operating at an AC frequency of 482.9 MHz has a voltage of n microvolt across its terminals. What is the value of n up to nearest? Okay. To find the voltage across this across the terminal of Josephson junction, what we have to do, we have to just use, and it is a superconductor. So what we have to do is this. It is basically energy conservation. H nu equal to Q V, where Q is the charge, V is the voltage. This is the required voltage that we want to find. But it is a superconductor, and superconductor they exist in Cooper pairs. So, and Cooper pair, it has 2 electrons. So 2e, so Q is equal to 2e for Cooper pairs. Q is equal to 2e. Now what we have to do, we have to find the voltage. So it is just V is equal to H nu over 2a. Let us now find this. V is equal to H nu over 2a. H is 6.626 into 10 to the power minus 34. Nu is 482.9 m. This is megahertz, so we have to multiply with 10 to the power 6 divided by 2e. So 2 times charge of electron is 1.6 into 10 to the power minus 19 coulomb. So what we have is 6.626 into 482.9 over 2 into 1.6 into 10 to the power minus 34 plus 6 plus 19. So this evaluates to somewhere around 999 point something into 10 to the power minus 34 plus 25. And this we can write as 10 to the power 3 almost. 3, and all these exponents we have 10 to the power, so this is minus 34 plus 25, it is minus 9. So it is 10 to the power minus 6 volt. So 10 to the power minus 6 volt is equal to 1 microvolt. So n is equal to 1. So therefore n is equal to 1. Okay, I hope this question is clear. We'll go to the next question. In an experiment, an niobium wire of radius 0.25 is immersed in a liquid area, and it carries a current of 300 ampere. The magnetic field inside the current, what is the magnetic field inside the current carrying wire? So here there is a bit of issue. So what it has, this question should provide what is the magnetic field, what is the magnetic field, critical magnetic field at 0 Kelvin. This data it is missing here. So we'll take V naught to be 0.2 Tesla. Okay, so now we'll solve the question with this data. So what we have to find is, we have a niobium wire and its radius is known. Radius is equal to 0.25 mm and 0.25 into 10 to the power minus 3 meter, and it carries a current 300 ampere is the current. What is the magnetic field inside the wire? Okay, and the critical temperature is given as 9.3 Kelvin, and we know that magnetic field is mu 0 I over 2 pi r. Okay, and we know 4 pi into 10 to the power minus 7, I is 300 over 2 pi into r is 0.25 into 10 to the power minus 10 to the power minus 3. So this will give me 2, and is, 6 into 10 to the power minus 5 will 10 to the power minus 4. So this will give me 5, which is nothing but 6 over 2.5. So it is 12 by 5. 2s are 10. 5 2s are 10. Wait, so this state is not 100. Okay, so what we have is we found that the magnetic field for this particular value of current, so at T is equal to 4.2, we already have this temperature, already have this current, magnetic field, V is equal to 2.4 Tesla. Okay, so this would be your answer. B is equal to 2.4 Tesla. So if the question would have, if it had a variation that what is the critical field at t equal to 0, then what you would have done is you would have to do this B at t equal to 4.2 Kelvin, which you already have as 2.4 Tesla, and then you can just use this B naught 1 minus T over Tc whole square. So with this formula you can find, like if the question asked in some other situation, then you could have got B naught as well. So for this question your correct answer is this one. Let us go to the next question now. Which of the following Josephson effects is used to generate and detect electromagnetic waves of frequencies ranging from radio wave to infrared wave? So if you want to, so electromagnetic waves are, these are basically oscillating electric field. Oscillating electromagnetic, and oscillating electromagnetic fields can only happen if there is an oscillation of these charged particles or charges around some mean position, and that can happen only in AC. Okay, so that is why you have to, so one has to use only this AC AC signals. Let us go to the next question now. So determine the temperature at which the critical field becomes half of its value at 0 K if the critical temperature is Tc. So we know the formula of how the critical field is related. Critical field at temperature T is related to critical field at 0 Kelvin by this formula. H T at some value of T, it is related to H of T equal to 0 Kelvin 1 minus T over Tc square of this. What we have to find? We have to find a temperature at which h of t becomes half the value of half of its value at 0 K. So we have to find half of its value at 0 K. So we just put it here. So this is h of t is equal to half of h at t equal to 0 is equal to h of 0 1 minus t over tc whole square. That's all we have to find. So it is 1 by 2 is equal to 1 minus t by tc whole square. So t by tc whole square is equal to 1 by 2, and this will give me t equal to tc by square root of 2. T equal to tc by square root of 2. So this is your correct answer. Let us go to the next question now. The magnetic susceptibility of an ideal superconductor is. For an ideal superconductor, okay, let us look at what is susceptibility. So we have a magnetic field induction value. The magnetic field induction value inside a material, it has to so it is mu naught times what is the magnetizing field. So suppose if there is a material, okay, some material, what we do experimentally is we put h, some magnetizing value h. So h is nothing but this depends only on the current that we are applying. Okay, suppose if we are looping a current like this, then h will be in this direction. For example, if we have a solenoid, it has let's say the number density of these coils is the n turns per unit length, and we are sending a current I, then the value of h will be parallel to this, and so this is h equal to mu naught times the current. Okay, so it depends only on the experimental setting. So h is what we have the experimental control on. So we can control the number of turns per unit length, and we can control what is the current we are sending. So given this magnetizing field strength, the material will the magnetic moment in the material, that might be due to spin angular momentum or orbital angular momentum, like whatever the reason may be, the material will there will be some magnetization induced in the material. Okay, that magnetization will get added to this h, and that will so the magnetic field induction due to the magnetizing field that we are applying is mu naught times h, and the contribution to this from the material property, the changes in the material due to this h, that is given by mu naught times m. So basically it is mu naught h plus m. Now one can define a quantity. You see this m, the magnetization, it depends on the material property, and it is a response to how much of the magnetizing strength that we are, or the magnetizing field that we are providing. Okay, experimentally we are providing this h, and the material's response to that is m. So in a very simple case, what happens, and it works for most of the material, this magnetization is most like for most of the materials it is proportional to the field strength that we are applying, or it is in the direction of the field strength that we are applying. For diamagnetic it is in the so it this the magnetizing field induction it will reduce, and for paramagnetic it will increase. So it is uh, like to separate out the contribution of the material property, what we do is we define something called magnetic susceptibility. So this magnetic susceptibility is defined as m. So this is actually a tensor of two rank tensor, but for most of the cases we use it as a scalar only, just a single value. And so if we just put this magnetic susceptibility in here, what we have is mu naught 1 plus chi h. Now this quantity is called magnetic permeability. And this is your magnetic susceptibility. Now what you have is for an ideal superconductor. In the ideal superconductor, what happens is there is no magnetic field inside the superconductor at all. So B has to be 0 for a superconductor. This means mu naught 1 plus chi h is equal to 0. See, this h we are experimentally providing. So whatever the uh, magnetizing strength that we are providing, you will still have this 0. We will still have that magnetic field induction inside it 0. And what that means is chi has to be exactly minus 1. So this quantity has to be 0. Mu naught is a non-zero number. It is 4 pi into 10 to the power minus 7. So the only way this can happen is that material property is such that chi is minus 1. So your correct answer will be this one. So these are the questions of your last week assignment. Probably that was the last assignment. And if you have any doubt in the questions or anything, you can ask. Thank you so much. And if you want to get the videos of the other discussions, you can get from this link. Thank you everyone.
Hello.
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 Yeah, I can.
Good evening, sir.
Yeah, good evening.
Sir, can you discuss some more problems related to your previous assignment questions or previous NPTEL questions?
Previous assignment question.
Yes.
Okay. Which one? I mean, you want to. Okay, okay. Yeah, that we can discuss.
12.
Assignment 12.
Yes, sir.
Oh, yeah, we can discuss. So, this is assignment 12 only.
So for this year, na?
For this year.
For this
Which
year.
question you want to see particularly?
This is clear, sir.
This is
Can you discuss some more assignment questions from previous year?
from previous year.
Yes, sir.
Okay. Previous year it is, I think, like for all the.
Or previous year questions.
Yeah. The thing is, this is the last week of the assignment.
Yes.
So the way I used to do was this. I'll just show you. uh, for example, in week 11, so it was of the last week, and there I had discussed uh, so the last week questions as well as wait, hold on. So last week questions and then the previous year question. But week 12 is said this is the last week, so after this there is nothing. So yeah, that is why since there are no questions anymore, these are the only questions we have. Like, but if you want to go for other sessions also, you can avail that in YouTube as well. uh, I'll just show you.
It is available.
Huh?
It is available, sir.
Yeah, it is available in YouTube. And what you can, I'll show you this thing also. uh,
Hello.
yeah, hello.
Yeah, sir, I wanted to ask about one doubt.
Yeah, tell me.
Well, there are questions like finding the magnetic field in a wire. You have done this question is right now in this session also.
Yeah,
So you are using the formula,
Missouri Iowa 2 pi r, that one, no?
B equal to mu naught I by 2 pi r.
Yeah.
Yeah, so sometimes even in the assignment I have seen sometimes the solution is given with H, sometimes it is with B.
Okay,
So
H
if
or
you
B?
use H,
Huh.
then we are just doing I by 2 pi r. We are not using the mu naught. So I am a little confused
Yeah,
when
yeah.
to use the B and when to use
Yeah,
the H.
see, it is just the same thing, okay? So, what happens is, this is week 12, okay.
Yes, means I know it's the same thing, but the answer is different. Means a mu naught, if you don't implement in the answer, the numerical value comes out to be different.
Yeah, yeah, that is true. I mean, so what it has, the question actually was a bit ambiguous in that sense, that particular question, okay, because it has
Yes,
not
yes.
asked, it has not particularly mentioned what is the magnetic field. So when it is magnetic field, when they are asking, we directly go for B, okay, and it is
Okay.
in Tesla.
Hmm.
uh, but this formula, no, this formula we can, since it is, this can be written as mu naught H and mu naught H0
Mm-hmm.
1
Mm-hmm.
minus T over Tc. So in questions, what you see, you have to look for what is the unit it is asking, okay. If this
Okay.
in some question it would be given such that instead of Tesla, instead of Tesla it will be using ampere per meter, okay.
Yes.
This
Yes.
ampere per meter is the unit of uh,
H.
this is the unit of H.
Okay. Thank you. Thank you.
Yeah. So based on the units of the question, you have to decide whether it is B or H.
Okay. So, thank you, sir.
Okay.
So, what kind of question will we get in the final exam, and how many questions will we get?
Final exam, I have no idea of the final exam. I think someone else is setting the question. So what I would suggest is basically go through all the assignments. It will be a similar type of question only. Okay.
Okay, sir. Thank you, sir.
Yeah.
Thank you so much, sir.
Okay. Thank you then. We'll end the session here. Thank you for joining.